All right, we're back, still talking about Coulomb's law and the force law, and now we're going to talk about the electric field at some given point that's caused by a charge that's anywhere else in space. So we're going to use the same example of two charges, except now we're going to go ahead and back up and we're going to say, you know what, I'm not interested in the force between the two, right? Which the force between the two was Coulomb's constant times Q1 times Q2 divided by R squared. And that was the equal and opposite forces of Newton's third law that's enacted by one charged particle on the other, and likewise the other on the one. So that's the force. Let's go ahead and figure out what the electric field would be where Q2 was caused by Q1. So what we're going to do is we're just going to ignore that Q2 even exists in this case 1. And we're going to find that the electric field at any given point in space caused by a charged particle is going to equal KEQ divided by R squared. Or you could also write it, as we did last time, as Q over 4 pi R squared epsilon sub naught. Okay. So these are two ways to write what the electric field is. And this is going to be the electric field at this point caused by this charge. And so R in this case is going to be the distance between our charge and where we're interested in measuring the field it's creating. Because of course if we move closer to the charge, the field will get much stronger because it varies as 1 over R squared. All right, so now for case 2, well actually let's take a look at this. So this is Q1, right? And if you'll remember, let's write it this way. A couple less constants there. So if you look between the electric field caused by Q1 at the point where Q2 is, you'll notice that it looks very similar to the Coulomb force between Q1 and Q2. And you'd be right. As a matter of fact, it looks like the only difference is that the electric force between the two includes multiplying by a factor of the charge of the second particle. So what we can do is we can multiply both sides here by Q2. So Q2 times E caused by 1, okay? I'm going to write it's the electric field caused by 1 at the location where 2 is. Q2 times E1 is equal to KE Q1 times Q2 divided by R squared. And so what we basically just proved here, let's ignore this case for a minute, is that the force caused by 1 on 2 is going to be equal to the charge of 2 times the electric field caused by 2. Q2 times the electric field caused by Q1 at the location where we'll place Q2. So this is a really nifty equation. It can save you a lot of time. Now next we're going to go ahead and talk about what the superposition principle is. And in order to do that, let's make a new example. So this time, let's say that we have a third charge. Okay, so we're going to get rid of some of these lines. Let's say that we have a third charge that's, let's say right over here, Q3. And we know the distance R between 2 and 3. We know the distance R between 1 and 2. And we'll say that we know the distance as well. And by the way, this is as the crow flies distance, right? So for the electric field, you're always drawing radially. As a matter of fact, I should have mentioned that. But it's kind of obvious when you look at the charge. So positive charges point electric fields radially in all directions. So actually, if this is Q1, the electric field is a vector that's caused by Q1 at any given point in space is equal to KE Q1 divided by R squared. in the radial direction. So you can go anywhere in space at some distance r. Let's say I go here and I go out here to this distance r. The electric field will be pointing radially outwards from Q1, assuming Q1 is a positive charge. Now, if Q2 is a negative charge, then it's what's called a sink. So a positive charge is the electric source, and the negative charge is an electric sink. And so if you plug in a negative charge here, you'll find that the vector E caused by this negative particle 2 is equal to KE Q2 over R squared, but Q2 is negative, and so it points in the radial direction but inwards, okay? So that's important. Between the two forces, the force between the two particles, just draw the vectors. And in this case, you can do the same because you know that the electric fields point in to a negative charge. So you could look here and just say, well, I know that it's negative, so it's going to point radially inwards. All right, that was a tangent. Back to our three charges. Let's say that we know a couple of angles. I'm kind of making this, we'll call this theta 1, 3, and we'll call this angle theta 2, 3. The reason why I'm making this kind of unnecessarily complicated is because I kind of want to show you what a problem of superposition looks like when you have multiple angles. But maybe the best way to explain superposition to start is that superposition tells you that if you have two forces acting on an object, so let's say I have some force 1 acting in this direction on this object, and some force 2 acting on the same object, and if I'm interested in the resultant force, these are vectors, so they add like vectors. So I move my tail to tip, I draw my parallelogram, and that's my resultant force, so that's F total. It both includes F1 and F2, so that's really all superposition is. So basically it's just remember that these things are vectors. Always remember what are vectors and what are scalars, and vectors add like vectors and scalars add like scalars. So yes, let's draw a picture here. Let's focus in on Q1. Okay, Q1, and Q1's negative. I'm going to make Q3 positive. So if Q3 is positive, then what would be the force caused by Q3 on Q1? Well, they're dissimilar charges, so they're going to attract. So Q3 is pulling on Q1, so this is going to be the force caused by Q3 on 1. And I want to point out that when you're focused on a particle here, you essentially just imagine, like I said before, all these particles are nailed to the board, so they're not going to move. So superposition tells us that you can focus on one particle at a time and find the forces on that particle. So this is force that charge 3 is enacting on 1, and then we see that this is more of a horizontal distance. So because forces act radially, the force is going to be radial to Q2. Once again, we have dissimilar charges, so we have attraction there. So this is the force applied from 2 onto 1. And that's also a vector. And those are all the forces that are acting on our charge Q1. All right. So we were given an angle here that's going to be useful. This angle was theta 1, 3. Now, using the alternating interior angle theorem, we know that if we have two parallel lines and a line that's cutting through them, that this interior angle is equal to that interior angle. So that's the alternate interior angle theorem. And so using that logic, I can say that this angle must be theta 1, 3. All right. So now, just like with forces and vectors and what we did last semester, we're going to need to break these into components so that we can add them. So force 3, 1 is going to be a vector that's going to have, well, it's going to have a length of, you know what, let's just say that because you're going to calculate the magnitude here by doing Q1 times Q3, right? Times KE divided by R squared. Okay, so Q3 is enacting on Q1, so we're curious about Q3, Q1. And then, of course, the magnitude, remember this is just the magnitude. All that Coulomb's force law calculates is the magnitude, it doesn't tell us the direction. So force 2-1 is going to look very similar. It's going to be KE, Q1 times Q2. Q2 is acting on Q1 divided by R squared. So from here on out, let's just, so we know how to calculate the forces here. So let's just imagine that we've already calculated those magnitudes and we're curious about the resultant force. Okay, so what I'm going to want to do is I'm going to want to find well, first I'm going to want to pick my orientation. Let's say X is right and Y is up. So I want to find the Y component of F of 3, 1. So F of 1, or F of 3 on 1 in the Y direction. And I'm going to want to find the X component of that vector, F of 3 on 1, X. Okay. And we know that this side is going to be opposite our angle theta 3, 1. And so opposite means sine. So we know that F3, 1x is going to equal the magnitude F3, 1. That's what those little two lines mean on either side of the magnitude. The magnitude of F3, 1 times sine of theta 1, 3. And that makes sense because sine is opposite over hypotenuse. If we divide this over here, then it says sine of 1, 3 equals opposite, which is F3, 1x, over hypotenuse, which is the magnitude F3, 1. So that's F3, 1. F3, 1x, here's F3, 1y, right? It's going to be very similar. Magnitude of F3, 1 cosine of theta 1, 3. All right. And then the beautiful thing about F2, is because we picked our x-axis in line with F2, we know that F2, is all in the x direction, and it's equal to the magnitude of F. The 2 is acting on 1. All right, so vector addition. We have all of our components. And let me make some room. So we have all of our components. So we just add the like components, right? The x's with the x's, the y's with the y's. Well, so F3, 1y, well, let's start with the x's. F3, 1x is the magnitude of F3, 1 sine of theta 1, 3. And then we're going to add the other x component, the magnitude of F2, 1. And this is all the x component. So x hat or I hat, whichever one you want to do. So this is going to be F, this is our resultant force. Total force on Q1 is equal to this x component plus, we know that the only vector with the y component was F3, 1, and that's just equal to the magnitude of F that 3 applies to 1 times cosine of theta 1, 3 in the y direction. All right, so this is the final force that's being applied on on the charge 1. So yeah, I hope that was helpful. I just picked that example because I wanted to be sure to incorporate angles, magnitudes, components. But yeah, all that superposition principle really is that you can figure out the force at any given point by combining the individual forces, and you can do the same with the electric field. So if you know the electric field caused by 1 on 2 and the electric field caused by 3 on 2, you can just take those and add them as vectors, and you'll end up with your resultant. And that's pretty much what superposition principle says. So hopefully this was helpful, and I'll see you next time.